All right, welcome all you good and faithful students to another video edition of ME 273. This is your host, Delgosa Han. We're going to be building a model together based on the Euler method. Oh, that Euler method is ancient. We're going to build an Euler method in the Excel program, a spreadsheet, and let's get started. As you can see in front of you here, on the slides, I'm in presentation mode. We're going to start by modeling a falling sphere with air resistance. This is not unlike the parachute problem you experienced in that chapter 1, but we're going to use a little more sophisticated drag force than what was used, right? And there's actually a reason we're starting with a falling sphere. You might think that this is a very simplistic thing to start with, and perhaps it is. Yet, as you'll see, and you're not going to see it right away, maybe in a week or so, you'll see what actually happens with a real falling sphere. All right, well, let's get started. There is a sphere. All right, before we build any kind of model of a falling sphere, we have to analyze the situation. So let's pretend, to make it interesting, let's say we're going to drop a sphere, let's say a spherically shaped object, let's say a basketball, right, or a bowling ball or something. Bowling ball might be more interesting. Let's say we're going to drop it from a really tall building. Why not the Sears Tower? All right. Yes, I know it's the Willis Tower, but it'll always be the Sears Tower for me. Okay, so don't correct the teacher. So we're going to go up to the observation deck, and we're just going to bring our bowling ball with us, and we're going to drop the thing. So this is where I usually ask all you brilliant students to guess how long you think it would actually take. Now we're going to model air resistance with a pretty realistic model, and so our model will be pretty accurate, not only in the algorithm itself, but also in the real physics that such an object would experience. The only thing we're not going to dial into the model, although it wouldn't be hard to do ultimately, is any lateral wind gusts. We're going to assume that our ball, our sphere, will fall directly downward in a straight line. All right? So we're going to drop this thing from really high height, okay? And so we need to analyze all the forces acting. We're going to apply Newton's second law, come up with the acceleration, and then all we need is a starting point. Since we're going to drop our ball, we'll just drop it from position 0. We'll call the down direction positive, actually. We can call it whatever we want. That'll be convenient for this problem. We'll call it positive, and so we're going to let the thing fall from position 0, and we're going to drop it so it'll start from rest. So once we know the initial position and the initial velocity at time t0, we have the acceleration, we'll have that from Newton's second law, we're ready to model the thing, right? So here is the ball, and let's say that this is a snapshot of our ball as it's falling from the Sears Tower. A snapshot while it's moving with some instantaneous velocity v, right? So we want to indicate what forces are acting on this thing while it's falling. All right, first of all, gravity is making it accelerate. We all know that. Force G stands for gravity. Gravity's pulling down. It's really toward the center of the Earth. Oops, I erased it. There's gravity back. Gravity turned off for a moment there. So it's back. And resisting or opposing the falling sphere, or the direction in which gravity is pulling it, is what we call the drag force. Now I have R here instead of D. I could have FD for drag. Sometimes it's called a resistive force, right? So that's the drag force, and it's pointing in a direction opposite of the direction in which the sphere is traveling. So the resistive force or the drag force is always in a direction opposite the instantaneous velocity, right? If it does fall in a straight line, these are the only two forces we have to deal with. So let's apply Newton's second law. We simply sum the forces up. Let's call the positive direction down, all right? And we'll call the up direction negative. So the direction the ball is falling in we'll call positive. And look what we end up here. Newton says to sum the forces, and that would on the right hand side give us the force of gravity, which is contributing a positive amount in the positive direction. The resistive force is opposing, so it gets a negative sign in the sum. Uncle Isaac says to set this equal to MA. Right? And here's the form of the forces we're going to use. Of course, we know if it falls close to the surface of the Earth, the weight, mg, is equivalent to the gravitational pull. That's essentially considering that gravity does not change appreciably over the distance it falls, and therefore you can take the force of gravity as a constant. And acceleration due to gravity is constant, multiplied by m, you get the weight. Here is the form of the resistive force we're going to take. Now this is something that you'll become more familiar with as you take courses in fluids and heat transfer. This is the form that engineers use for a typical drag force, and also the form that's used in wind tunnel experiments, whether it's traveling fast or not. Now, there's no magical form of the drag force. So you may remember back in that chapter 1 with the parachute problem, it was assumed that the drag force was proportional to the first power of velocity, right? Now, it should make sense, it should make some physical sense that a drag force should be proportional to some power of the velocity. It's just not particularly obvious what power that should be. The faster you move, the more of the fluid, in this case, the more of the atmosphere you're bumping into as you move, and therefore the drag force should have some proportionality to velocity. We're going to use v squared. Again, this is not a theoretical model for air resistance. This is more empirically determined, and seems to work. So we're just going to use it. I'll show you where it breaks down later, but we'll use the resistive force or the drag force proportional to v squared. Now look at the other three terms in the drag force here. There's a d, lowercase Greek rho, and an a. Right? These are, and I think I have them defined here, d stands for drag coefficient. This is actually a unitless quantity. We are going to assume for our first model we build together that it has a specific value of 0.5, and we're going to assume our sphere is not spinning. All right. This comes from experiments, and eventually I'm going to show you where this comes from. But in general, the drag coefficient is not constant. We're going to start out assuming it's constant, but even for a smooth sphere, as we'll see soon, it really is not constant, and it depends on a lot of things. And so we'll start out assuming it's constant. We'll tackle the simplest case, and then I'll show you how to deal with things when they get ugly. All right. And by ugly, I simply mean that d itself, this d here, can itself have a velocity dependence, and a complicated one at that. Right. The next thing is rho. That lowercase rho is the density of air density, right? Which we know. It makes sense that the drag force, or the resistive force, should also be proportional to rho, because the more dense the fluid, the greater the resistive, or the resistance, or the drag on the thing that's moving. Finally, A here is a cross-sectional area. Sometimes in some engineering books you see the term frontal area used. This is the area that the object presents, a cross-sectional area that's presented in the direction in which the thing is traveling. So for instance, if a sphere were thrown directly at your face, which let's hope that never happens, but if a sphere were coming at you and you could actually look at the thing, it would look like a circle coming at you, right? That would be the cross section that you would see. If let's say a non-spinning cube were thrown at you, you would see a square. Okay, so that's the cross-sectional area, or the frontal area, presented in the direction of travel. That also makes sense that it should be proportional to A, simply because the bigger the object, the more area presented in the direction it's traveling, the more stuff it's going to bump into, the more fluid will push against it. All right, and finally, m is the mass of the sphere. So those are all the parameters involved. So if you put this form up into here for the resistive force, put mg for gravity, and solve for A, Very easy algebra. Okay, those are the forces inserted. Solve for A. Now in this last equation here, I've put back that functional form, A of t. All right, now look what you end up with. A equals G, that's a constant, D rho A over 2M, those are all constants defined up here. But you'll notice it's times V squared, V of t, so I'm indicating that the acceleration is indeed time dependent because V inherently depends on time. A depends directly on V here, depends directly on V squared. But of course this ball is falling from the Sears Tower and it's picking up speed as it falls and it's moving, its position is changing. And so V will also change with time. So here's an example where A does depend on time, but it doesn't depend explicitly on time. It depends explicitly on the time-dependent variable, or the time-dependent quantity, velocity. All right, well look, we're equipped with the acceleration. Newton's law gave us this, and this is the function we're going to use. We know if I plug in any t, actually any v at some t here, then I can get what the acceleration is. All right, all I need now is the initial conditions. That means the initial position and initial velocity where it's located, and I can actually do the approximation now. I can solve this differential equation now with the Euler method. All right, now before we go to build the Euler method model and do it numerically, I want to point out you can actually integrate this thing. Believe it or not, you can let dv, A equal dv dt, separate the differential equation. I'm not actually going to do it for you. I'm just going to show you the answer. You could look this up. Wolfram alpha. Type it into Wolfram alpha and it'll show you what the answer is. Right? If you integrate the thing, you actually do get an exact solution. dv dt equals this stuff. Solve that differential equation, which means you integrate it, and you get v equals this. By the way, the initial conditions I used for this was v is 0 at time 0. So if you put a 0 here, this is a hyperbolic tangent function. Hyperbolic tangent of 0 is 0, so the whole thing is 0. So the initial conditions are at t equals 0, initial time, v is 0. Right? And guess what? You can integrate this again. Right? Integrate it again. V is just dx dt. Let's use y instead of x. Let's use dy dt, y for a vertical direction. Integrate this again. Now it should not be, if it's obvious to you, then you are geeky beyond help. All right. If it's obvious to you that this is integrating the hyperbolic tangent gets the natural log of a hyperbolic cosine, all right. Trust me, this is what comes up. Right. You can integrate this thing, and you get this horrid looking function. Now, why am I integrating this? Remember, one of the points I've been making all along is, in a realistic physical situation, the integrals likely don't exist. Now, this integral exists. We can integrate it like this to get v and y because we're assuming d is constant. If d were, as I've said, to take on a complex velocity dependence, the jig would be up here and we couldn't integrate these things. But keeping d constant gives us the luxury here of when we build our Euler model, we actually have some exact solutions with which to compare our numerical or our computational model. And that'll give us some insight into what the error in our numerical solution is. All right, so we'll make a comparison. And this is very similar to what was done in that chapter 1. So it might be worthwhile. It's up to you. You don't have to do this. It might be worthwhile to go take a peek back, stop the video, go back and read through that parachute problem in chapter 1 of the book, because it takes almost the very approach we're going to take here with the Euler solution. It's just I'm going to walk you through it and give you a little more detail here. All right, well, so this here, this A of t, this is our acceleration. We have the initial conditions. And so we're going to apply the Euler method, and I'm just going to show you the Euler method again on the previous slide. Back here so you remember what we're doing. And that doesn't have it. There it is, right there. This is the version for v, remember. So the Euler method equation here. Now the Euler method itself involves iteratively doing this over and over again, but this is the equation we're going to apply. The velocity at a later time, some t plus delta t, is approximately equal to v at the earlier time plus a. We have a. Newton spit that out at us. We know what a is, so I can evaluate a at any time I choose because I've got the function. So I've got the exact function of a. It's just we're going to be plugging in different times into it. Right? Well, actually different velocities that we've approximated because remember a depends on v. So we're going to use this equation, and we're also going to use the version for y. Remember, I think back here somewhere, we did the Taylor series version, and you can do the same thing for y. Although that's that equation that I need to correct. That's not the right one. Anyway, we'll get to it here. Right? So I'm going to get out of presentation mode, and I'll put it here if we need to look back at this for any reason. And I would say it maybe the best way to do this is to fire up a spreadsheet and do this as I take you through it. Build the model along with me, or watch through the video and then build it later. Try it cold on your own. Just some suggestions on how to go about maximizing your experience here. We're going to build this in Excel first. Then your assignment is going to be for you to build a MATLAB version using this as your guide. All right. First step is to define or to build this control panel. So in the upper left, I'm going to make a list of everything we're going to need. Right? All of the parameters we're going to need to build the model. Right? Now, one thing that's going to play a very important role is a delta t. All right? Now, I think at this point, I'm going to, instead of writing out delta underscore t like I've done a couple times now, I'm just going to put dt. All right? Don't let that confuse you. That is not an infinitesimally small quantity. It's really delta t. It's just I want to keep it short and sweet here. All right? Just dt is easier to type in than delta t. Okay? So we know what that is. That's our time step. Or our delta t, that's the time interval, that's going to remain constant, and that's how far apart all the time steps are going to be, the different times in our solution. Right? So remember, we're not coming up with a continuous solution. It's not going to be a continuous function. We're going to only come up with solutions at specific discrete times. And every one of these times at which we arrive at a solution will be separated by this value of dt. All right. Now, what else do we need? We need an initial position. Let's go ahead and define an initial position x0. Even though we'll put these at 0 to start with, let's just define it this way because we can always change these. Right? v0, v underscore 0 is the initial velocity. All right. And if you look back at that slide quickly, we need 1, 2, 3, 4, 5 more things. I'm going to call these the parameters, the physical parameters we need. We need good old friend g. That's acceleration due to gravity. We need d. Remember I said we're going to start out with 0.5, so that's just a constant. We need to know what the density of air is, close to sea level. And we need to know what the area of our ball is. And so we'll have to decide what kind of ball we're going to drop. All right, so let's go back and put those in. So I need a d. Excuse me. I'm actually going to write out the word drag for the drag coefficient. Sometimes spreadsheet programs don't like you to use a single letter because then they think you're trying to call something about a specific column. All right, so I'll just call d drag instead of capital D. We need a rho. Just type out rho, R-H-O. That's the density of air. We need area. Now, let's think about this. It's going to be a sphere. All right, so we could calculate, we could figure a radius of a sphere. Remember, this is the cross-sectional area, so if it's a sphere, it means it's a circular area presented in the direction it's moving, so I would have to have pi r squared here for the area. Why don't we do this? I'm going to suggest let's just indicate a radius. This way we can indicate a radius or a diameter, for instance, of a ball that we're interested in dropping. And it will be really easy to change in the control panel if we just change a radius rather than calculating the area. And we can actually calculate the area that we're after directly here. So I'm going to type out the word area. That's going to be that A, right, and radius. And then when I calculate this, I'm just going to let area equal to whatever the radius is square it, and then multiply it by pi. You'll see when I get to it. So drag D, rho, A. We need gravity. That's GRAV. Again, I'm avoiding just using a single letter. You probably could get away with it. Certainly in MATLAB you could get away with it. It's just the spreadsheet's a little funny if you use single letters, so that's why I'm sort of spelling these out a little bit. And mass, M-A-S-S, right? Okay, so that's all we need. If you look back just to make sure. Okay, and so now remember we need to define all these things in the boxes right adjacent to the labels here. If you were going to be thorough and hand this in, for instance, for somebody to look at and grade, or if you were going to share this with somebody and you wanted them to understand what you're doing, you would probably take a little more effort, and maybe before you actually defined what the variables were, you might actually label these in the adjacent column. So for instance, you might say this is the time step in seconds, initial position, initial velocity, drag coefficient, density of air. You might just this is what I would do if I were creating a nice, beautiful, polished spreadsheet that everybody could follow and understand. Let's not take time and do it right now, though. You could always clean this up and make it look really nice later. So starting in the box adjacent to my time interval, delta t, right? I'm going to go up, highlight the name box, and type in exactly what I have for the label there. This way, if I define the variables identically to how I have the labels in column A defined, then there's no confusion as I program things. All right, don't forget to hit enter. Okay, and then go to the next row, go up to the name box, define x_0, enter, and do the same all the way down. So I don't really need to keep talking as I do this, I suppose. v_0. All right. Always hit enter before you move that box anywhere else, because it can kind of screw things up. By the way, if you do get screwed up, if your names and variables do get screwed up, there's at least on this version of Excel, there's a formulas tab. See, I just hit that there. And there's this thing called a name manager. You can also get to it, Control F3. And if you open that up, if this comes up, this is a way that you can fix all your variables. Matter of fact, you could just insert them all in directly here too. You don't have to use that little name box up here. But however you want to do it, right? There's many ways to accomplish the same thing. Not only in a spreadsheet, you'll find this in MATLAB too. You're all going to find ways to do things much better than I do. Right? So I would say feel free, play with things, be resourceful, and do it however you want, as long as it accomplishes what we're out to accomplish. So let's continue with the rest of the variables here. Drag. Excuse me. This one is row. Oops. What the heck happened there? Try again. Row. You'll see what I'm doing with this radius thing. That'll be obvious in a moment here. Radius. Area. Gravity. Finally, mass here. Mass. Excuse me. Okay, now let's put numbers in, and then we'll do that little check like I've tried to demonstrate for you before, because I don't want to move on until I'm confident that all of these variables have been properly defined and the spreadsheet knows which one I'm wanting to use. All right, so let's put numbers in. I'm just going to start with 0.1 just to give it something. And we said we're going to drop it. We're going to drop the ball from position 0. That means the pavement, at least if I were on the observation deck, I believe, and we could look this up, but I believe the observation deck is something like 440 meters above the pavement. So if I drop it at 0, that's the initial position, then it will hit the pavement when the position gets to 440. Right? That's what we're looking for. We're going to drop it. We could throw it downward. Well, let's just drop it to start with. We can always go back and change that. Remember I said we're using 0.5 for the drag coefficient. Stay tuned. You'll learn all about that later. Rho, what's the density of air close to sea level? It's about 1.29 kilograms per cubic meter. Yeah, I know. It's really nerdy that I know that, but, well, tough. Now, here's where we got to decide what kind of ball we're going to drop, right? Um, why don't we start with a basketball, see what happens, all right? And I don't know, what is it? Let's just look it up real quick here. Radius of a basketball. You can learn, you students have so much information at your fingertips in this day and age. All right, so the ball is called a basketball. What is an orange? Yeah. A men's ball is about 9.55 inches, and a women's ball. But did you know that? I don't know if anybody of you realize that. Has anybody ever played basketball with a women's ball? I used to go over to it was the old gym. It's long gone now. When I first got to Bradley, some of the women in the athletic department would play. We'd have a pickup game, and you know, I don't mind playing with women. Actually, they were kind of tough. Uh, but we would always use a woman's ball. Man, I could pop from 3-point land. Holy cow. It's like somebody gave me a softball to use and shoot with. Oh, man, I could pop. I could even palm the thing, believe it or not. Right? Yeah, so much for equal stuff. Right. Anyway, so look at this. I don't know. It doesn't matter which ball we use. So look, you'll notice that the diameter of a men's ball is about, I'll round it down to 24 centimeters. That's the diameter, so that's 0.24. You divide by 2, you get 0.12 meters for a radius, right? So let's just use that. Close enough, 1.12. So where are we at? Point. So that's what I'm going to use for the radius. 0.12. So keep in mind we're using MKS units here, metric units, right? So this is in meters. Right, now here's the area. Remember, we went to I want to be able to just, I don't want to have to calculate the area directly. We may as well use the spreadsheet to do that. And so if I just specify a radius, I can put the formula right in here. So let's assign this box where area is defined. Let's assign it. Equals means assign. Now you could just put in 3.14. That would probably be enough accuracy what we need here. 3.14159, you know, all that. Or there actually is a pi, and I believe I type in pi. Do I do it? I think I got to do this. Oops. I think I got to have empty parentheses. Well, here, let's just test it. Yes, that does it, right? See that? Now, after you program something, you go back after you hit enter, you can always go back and double click and it shows you what you programmed. So pi with open and close parentheses with nothing in it returns pi to so many, I think it said 15 digits or something like that. It's a double precision number, by the way. Times, so that's pi r squared times radius, upward pointing arrow 2, right? And so you can see it's using the radius in the box above. So pi r squared, that is the cross-sectional area of a basketball, a men's basketball, I guess. Well, close. Right? Okay, gravity, on to gravity. We could use 9.81 if you wanted to. Remember the down direction is positive, and so, but g, little g, always is a positive number. The weight may be plus mg or minus mg depending on the direction, but just keep in mind this parameter is always a positive parameter, right? Now, what is the mass of a basketball? Let's look that up real quick. I should know this, but I don't remember. Of basketball. I didn't put mass, did I? So that's nice. MAS, there we go. And 0.625 kilograms, right? Regulation NBA basketball is let's use that, okay? 0.625. All right, so those are all the parameters. Now, that's my control panel, and I'm just going to go somewhere and just check that all those values are indeed stored properly, that the computer knows what that the spreadsheet knows what all my stuff, all my variables are. All right, so I'm just going to go down the list. Equals dt. I'm just assigning each successive box everything down the list. X underscore 0 looks good so far. V0. You'll notice it's color coding it for each one I choose here. Equals drag. Yep. Equals row. Okay, it looks like I got everything defined well. Equals radius. Equals area. equals gravitational constant, and finally equals mass. Yeah? Okay, good. All right, so that the control panel is set. We're ready to program things. So let's just get rid of all those values. Highlight them, hit delete.